Yes, so the recording has started. So guys, please confirm once again that my screen is visible.
Yes, sir, it is visible.
Okay, thank you. So good morning. So in today's class, we are going to discuss about this load line of this BJT of an like of a circuit using a bipolar junction transistor or BJT. In the last class, we have seen like how to analyze a DC, DC circuit consisting of a bipolar junction transistor. Right. So we have also seen like how to means what should be the way that we should proceed, and we have also seen if this transistor is in saturation, then that V of C sat value will be given to us, and if we know this V of C sat, then we should be able to find what is the IC, IB, and all this means the voltage drop across the required voltage drop as well as the currents. Right. So we know all this stuff now. Just to recap before we start this thing, so um, to proceed with this DC analysis for a BJT circuit, we have to first assume that the BJT is in forward active mode. Considering that, we have to see to take this V of B. Obviously, here we are considering this NPN bipolar junction transistor. We have to consider V of B equal to V of B on, and that is equal to nearly 0.7 volt for silicon BJT. Then IB, we have to like IB is greater than 0, and then IC would be beta times of IB because we have assumed this is in the forward active mode. Then you have to analyze the circuit, and finally you have to find this V of C. If this V of C is greater than V of C sat, which is around 0.2 volt, then it is in the active region. And if it is so, if we are getting the result that V of C is greater than V of C sat, then obviously our assumption is correct. Then we can proceed with this formula that IC equal to beta IB and calculate the required voltage drops after finding IC. But if we find that V of C is less than 0, then probably we have to see that the transistor is operating in this saturation region, and we have to consider the saturation region and find the other voltage drops. If this IB is less than 0, then probably the transistor would be in the cutoff region. Right. So this is the basic thing. What this is what we have discussed in the last class. Now, say in today's class, let us discuss about the basic load line. So this load line we are also familiar when we have done the our diode circuits. There also we have this concept of this load line, and load line basically will help us in visualizing the biasing conditions of a particular circuit. Right. So, for example, if you see this circuit here, this is base is forward bias by this voltage source VBB and RB, and this collector to base junction is reverse biased by this voltage source VCC, and this RC. The RC is the limiting current, limiting resistance. Right? So here we can also see the polarity of this VBB, and from this it is clear that it is in the active region only. Right? It is forward bias only. So if it is forward bias, let us proceed step by step. If this junction is forward bias, right, then obviously we can take or draw one load line in this using this in this loop, right? And if you do so, so we can see it from here, like this V of B. If we plot V of B, that is this voltage, this voltage, right, and versus this IB, that is the base current, then obviously we know this is nothing but this will be a diode similar to the diode type of characteristics. So we know the characteristics of this IB versus V of B would be like this, right? And then if you also plot means take the equation or make this KVL, write a KVL equation along this loop, then what can we write? We can write from here that the VBB would be equal to IBRB plus V of BE, right? Or in other words, if we say like what is the value of this IB, then we can write IB will be equal to VBB by RB minus V of BE by RB, right? Now, if we consider the thing where this IB is equal to 0, right, means along this x-axis. So if you put IB equal to 0, then we find V of BE will be equal to V of BB. So here, this is the point where IB equal to 0. So this, the value of this point is obviously this is V of BB, right? And then what about this point? Then here you have to put V of BE equal to 0. So put V of B equal to 0, you will find IB will be equal to this V of BB by RB. So this is that point, right? This is the value of this IB here. And you know this intersect of this load line and this characteristics, this green characteristics is basically the Q point of this input section, right? So here, this is the Q point or this quiescent point, right? Q point. So here you can see this Q point depends on like the characteristics of this in this PN junction, which is if you change the doping and this stuff, then what will happen? These characteristics will change. So that way this Q point might change. And the other way would be if you change suppose VBB, then if you change VBB, keeping everything constant, then this point will also change. At the same time, this point will also change. So that will also change the Q point. Similarly, if you change this RB, all right, this resistance, if you change this RB, then also this point will be fixed, but this point will change the position of this point, and that will also change this Q point, right? So so this is the way by which means or these are the parameters from which we can. So let me write here this RB, GBB. Primarily from the circuit point of view, only these two, right? Because we are saying that this transistor is transistor is fixed and we are not changing the property of a transistor. Then if you change these two parameters, then this Q point will change, right? So from here, what the values that we will get from this, we will get from this, what would be the value of this V of B, exact value of this V of B, and what would be the value of this IB, right, from this characteristics. This is BE junction characteristics, right? Okay. So this is from the input side. So similarly, if you are interested, you should be also able to find a load line along along this loop, right? This output loop. So and if you do that, here the output current is IC. So the output current is IC, and this output voltage is V of CE, right? Output voltage is V of CE. So here, if you plot this V of CE versus IC, then you know that here two things you have to plot. One is the transistor characteristics and the other one is the load line. So IC versus V of C characteristics would be like this for different values of base current, right? This IB1, IB2, IB3, we are already familiar with these characteristics, right? This is the output characteristics of this bipolar junction transistor. Now regarding load line, again we have to write the the basic equations along this output loop. So if we do that, it will become VCC. Let me write it in a better way. It looks like V of C, V of CC, right? And that is equal to IC RC plus V of CE, right? So similarly, like here, what we have done, if you take this IC, write this IC, that would become this VCC by RC minus V of CE by RC. Right. So here, if you keep if you make this IC equal to 0, which is basically this point, IC equal to 0, then V of C become this VCC only, right? So obviously, then this point is VCC only. And if you make V of C equal to 0, which is basically this point, right? So keep V of C equal to 0, that will make this IC equal to VCC by this VCC by RC. This is this point. So if you know you have now you have these 2 points. If you connect these 2 points by a straight line, that would give you this load line, right? This is load line along this outer loop, right? Then the intersection of this load line with the output characteristics would give you the Q point. So for example, if your operating current or this value of this IB is IB1, then this Q point would be this one, right? If you're now if you increase this base current from IB1 to IB2, then your Q point would be this. If you now change to IB3, like that it will change, right? So please note one thing, that when you are starting, right, means when the base current is increasing, like above cutoff. Okay, say first cutoff when this IB equal to 0. So when IB equal to 0, then basically IC is equal to 0. So that is basically, this line, right? This black line only. And so this black line have an intersect with this load line at this point. So this Q point would be here, right? So you can see that when this transistor is in cutoff, so V of CE would be equal to V CC, right? So that means IC is equal to 0, so the entire V of CC would be drop across here. So that is also you are getting from here. Now, if you are started increasing this IB, this Q point has started shifting from this point to this point to this point to this point, right? And see, notice what is happening. If this IB1 is less, right, then what you are getting from this Q point, that this is the value of IC, right? And this is the value of V of CE, right? This is the value of, say, V of CE1 for this, and this is the value of this, say, this IC1. So you increase this IB1, IC1 is increasing, and V of CE is reduced from VCC to VCC1. Now, if you are going to this place, IC2 means the IC will increase, say IC will go to IC2, and your VC will further reduce and will become VC of E2, right? Say, and see, this is also expected from here, because as you are increasing IB, so IC will also increase, right? As you are increasing IC, the drop across RC will increase. As this VCC is fixed, so then V of CE would also expected to reduce, right? So that is what you are getting, right? From this load line. And see, from here till this point, right? From here means from this Q point, to this Q point, and the transistor is operating in the forward active mode, right? This from here to here, right? Now, if you suppose that is, say, like IB5, right? Now, if you further increase this IB, say IB6, then this will go to here, right? So that would make, so the transistor is no longer now in the forward active mode, but it is, the Q point is now in the saturation region, right? Now, suppose if you have an further one more region, okay, if you can, like, you can obviously add one after that, no issue. Suppose if you further increase this value, IB, say IB7, right? And now see the intersect, this is still in this saturation region. So if you go beyond this point, then your Q point would be in the saturation region. Right. So this is the concept of Q point from this load line, and you can see it is quite easy to visualize how this IC and V of C would change with with change in the other parameters of the device, or the current, the base current, right? So this load line is generally used for visualization purpose, to to see, like, how the other parameters would change when we change one or two parameters simultaneously. Right. I hope this part is clear to you. This is similar to the PN junction only, diode only, load line. Right. So this is for DC analysis, and this is called the DC load line. So we will have something called AC load line as well. That is for some that we will discuss during the AC analysis. Right. But this is only for the DC one. So here you can see everything is like no AC source is present, right? Everything is DC. Okay, so if this part is clear to you, then maybe we can do this thing quickly. Yeah. So see this circuit. Here we have to find the Q point. Okay. So please try to do this with me. Okay. Take your pen and paper and try to solve this. See, you have to find the Q point, right? Question is this one. So here there are two voltage sources, right? Supply source. One is this V1 and the other one is V2, right? V1 is plus 5 volt, that is supplied here, and this V2 is minus 5 volt. Right. Remember, here we have an RC, which is a resistance connected to the collector. At the same time, we have an RE, that is a resistance which is connected with the emitter terminal, right? And at the same time, see, this base is being grounded, right? So now you have to analyze, like, and check how this circuit operates, and what should be the mode of operation for this circuit. Yeah. So any idea how to start with?
Sir, base emitter is in Reverse bias.
Base emitter is in reverse bias. Is it in reverse bias, base emitter? Please check it.
Oh, no, sir, no.
Sir, forward bias.
Yes. If it is reverse bias, then it will be in cutoff, na?
Yes, sir, it is forward bias.
Yeah, it is forward bias. Then how to start? How to find this Q point? Q point means basically what you have to find primarily this IC and V of CE, or ICQ and V of CEQ. So how to find? Say if we consider this loop, okay, this loop from ground to this loop, then we can write one KVL na, along this loop, right? So what would be this KVL? So KVL is like here this VBB equal to 0. So we can just write start with 0. This is equal to this V of BE on, right? This voltage V of BE on, right? And what is this current? This current is IE, right? Plus IE RE, right? Plus this one. So plus this means plus V2. Plus V2 means actually here it will be minus, right? Minus of 5 volt. So that makes this loop, right? KVL along this loop. Is this fine to all of you?
Yes, sir.
Okay. Then from here we can easily find what is the value of RIE, right? If other things are given, say this V of BE is also given as 0.65 volt. Okay. If this is given, we can also find IE. So can you please find IE from here? Please tell the value of IE here.
Sir, 4.35
Okay, very good. 4.35 unit.
units are milliampere.
Ah, very good. So 4.35 milliampere, right? Exactly. Now, if you know IE, then you have to find this IC. How can you find IC from IE? How can you find IC from IE?
Alpha
Sir,
times I.
alpha.
Alpha times IE. So this beta of the transistor has to be given, right? Say this beta of the transistor is given as 100. So if this beta is 100, then if this beta is 100, what would be the value of alpha?
Sir, 100 by 101.
100 by 101, right? Yeah.
Yes.
And what will be this value?
0.99.
0.99. Okay. If it is 0.99, then what would be the value of IC? 0.99 into IE, right? Then can you,
4.307.
huh?
4.307 milliampere.
4.307 milliampere, right? So you know now this IC. So if you know IC, then you can also find V of CE,
Yes, sir.
right? So what would be the value of V of CE?
So we have to write like KCL.
KCL or KVL?
KVL.
KVL along this loop, right?
Yes.
Okay. So let us, so you have to find this one, right? So let me write this KVL as well here. So you have to find this one, right? So what will be the KVL? So let us start with this V1 plus IC RC plus V of CE plus IE RE plus this V2, right? That would make this thing equal to 0, right? From here, we have to see everything is known except this V of CE. So could you then please find what is the value of V of CE?
Sir, it's approximately 3.5.
It's approximately 3.5. Okay, you are right. It should come around that value only. V of C, this right? So what is the then Q point? Q point is IC. This is the one of the Q point, and V of C, this is the another Q point, right? If like if you consider this Q point to be only this, right? From this output characteristic. So this is anything this Q point, right? But if you consider it from here, then also you will have a Q point which is IB. So that is also quite easy to calculate, like, because if you know IC, you should be able to calculate IB, right? So here you notice that in some cases you might have given this type of circuit where you have two different supply voltages. One is the positive supply voltage and the other one is negative supply voltage, right? And if you see in some case that the base is grounded, right, even for PNP or NPN transistors. So please do not just straightforward come to the conclusion that the transistor is in the cutoff region, because see, for here as well we have seen the transistor is not actually in the cutoff region, right? You see this. First thing is that we have a finite value of IB, we have a finite value of IC, that makes sure that it is not in the cutoff region. And then we have assumed that obviously when starting when we are writing this thing, then also we have assumed that the transistor is operating in the saturation region, and right, that if the transistor is operating in the saturation region only, then only we can write this, right? Because then only the concept of this beta is coming, right? And see from here that V of C we are getting 3.5 volt, which also makes confirms our assumption is correct, right? So this is the way
Sir?
you can. Huh.
Sir, what will happen if the base emitter junction is in reverse bias?
Yeah, then can you please answer to this question? Base emitter junction, base emitter junction reverse bias, then that means IB would be either 0 in one case, or you might find IB equal to negative, right, for NPN transistor. So for NPN transistor, IB cannot be negative. So that way, then the transistor would be in cutoff. So you see this, right? We have either you will find IB less than 0, or you will find IB equal to 0. Then the transistor would be in cutoff. Is it okay?
So the second KVL I did not understand how you wrote. Means V1 minus ICRC should be there, no?
Right. Or then in that case, will it not be easier?
Sir,
Like,
it would be equal to V1 is equal to the whole statement.
yes. So then it would be easier to maybe correct it like this. Can I make this change?
Yes, sir.
Is correct, right? No?
Yes,
You
sir.
are,
Yes.
yeah, absolutely, you are absolutely right, because it is a positive source. So it is like V1 equal to this one, or I can write like minus of V1 because we are starting from this, and we are good. Is it fine, right?
Yes, sir.
Okay, thank you. Now here is one interesting topic. This is also somewhat we have discussed during our PN junction analysis, circuit using PN junctions there as well. So this is nothing but the voltage transfer characteristics of bipolar junction transistor. So voltage transfer characteristics means when you see this transfer characteristic, transfer means basically something like output by input, right? And voltage transfer means it is output voltage versus input voltage characteristic. So you can see here output voltage is V0, input voltage is Vi. So you have to plot how V0 is changing with changing Vi. Right. So the circuit is say like this as given here. So Vi is the input voltage which is given here, as you can see from here. And the output voltage, say we are taking from here, right? From the top of this collector terminal, right? So this is the output voltage, and you have to make a plot of V output versus V input. Okay. Now, first thing is that we have to like do this analysis step by step. First thing is the case one, when this see, first you have to start Vi from 0, right? Vi will start from 0, and then slowly this Vi will change, and this Vi will VI can go maximum up to this supply voltage, that is this VCC, right? 5 volt. So VI start from 0 volt and it will go till 5 volt, right? So, but see from here, when this VI is 0, then this transistor is off, right? Because there is no base current. This junction is off. There is no base current, so it will be in cutoff. Eventually, this cutoff condition will persist until and unless VI is greater than 0.7 volt, right? So VI from 0 till VI less than 0.7 volt, right? So this would be in the cutoff region, right? If this in the cutoff region, then we can write IB, IC, like all of them are equal to 0. So if IC equal to 0, then this is basically IC, right? If IC equal to 0, then there is no drop across this RC. Then what would be this output voltage? See, this output voltage is
Phi.
nothing but this V of C. Yes. You
Sir,
have a
why,
question?
sir?
Why?
Sir, because there is no drop between 5 voltage and RC. Means there is no drop in RC. So 5 voltage would be V0, no, sir?
5 voltage, 5 voltage would be V0. Where is 5 voltage?
Sir, the above 5
Is
voltage, the topmost.
here.
Yes, sir.
Okay, see, in any case, KVL, oh, okay, sorry, it got clashed. I don't know whether it is saved. 1 minute, huh? Oh, if it is not saved, then I will be in trouble. Yeah, it's somewhat been set. Wait. Is my screen visible?
Yes, sir.
Okay. Yeah, see, in any case, this KVL has to be you have to follow this KVL, right? So if you follow this KVL along this, right? So how can you write this? This is 5 volt equal to IC RC plus this V of C, right? This is basically that V of C, isn't it? This is plus minus if you say it like this, right? Then if IC equal to 0, right? Then what you can write, V of C equal to 5 volt only, na?
Yes, sir. Means I was telling that V output is 5 volt. Means
Yeah.
indirectly it is that only. Yes, sir.
Okay. Yeah. Then you were right. Yes. Then you were right. Okay. So if this VI is 0 within from 0 or starting from 0, and if we consider VI till less than 0.7, then the transistor would be cut off. Then this IC would be equal to also 0. That makes V output to be equal to 5 volt. Right? Okay. So we have understood this part, and let us first draw this part as well. Okay. So I see this is 1 volt, 2 volt, 3 volt. Let us write this 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, right? So till 0.7, 0.7 is somewhere, say like here, till 0.7, this output is like 5 volt, right? Till 0.7, output is 5 volt. Okay. Then what will happen if you now increase this input voltage? If this VI is greater than say 0.7 volt, what will happen? The transistor is on, right? Definitely transistor on. So, okay, now can you comment in which mode of operation transistor would be? Guys, please answer this question. The transistor would be in which mode?
Active or
Active or saturation? If active, which mode?
active.
Why?
VC is already 5 volt, so VB is less than.
Okay, you can think from that point of view, and the other point of view is that, see, if this VI is less, means just above 0.7, right, then this IB would be also less, right? If this IB is less, IC would be less. If this IC less, then the V of CE would be and significant a positive number. That is one way you can explain this, or maybe you can also consult this image for this, right? This figure for this. So you can see that as we are increasing this V of V input voltage, basically here this VBB, then what will happen? Slowly we are increasing IB, right? So IB first this, then this IB2, IB3. So basically you can see these points, Q points are from here, 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 going like that, right? So in this entire region, the transistor would be in the active forward active mode only, right? So that is another way by which you can also consider like explain this. So from this you can write BJT is in forward active mode. If this BJT is in forward active mode, then what will happen to its like IC? Before I go to IC, what will happen to its IB? IB would be equal to VI minus VBE on by RB. Is it fine? This equation, right? The base current IB would be equal to this VI minus V of BE on, right, by RB. This is value of IB. So if you now know IB, you can also find the value of IC. It will be like, because it is in the active region, so it will be beta times of IB. So it will be beta times of VI minus VBE on by RB. Right? This is how we can find IC. Now, if you know IC, you can also find this V output voltage. So what will be the V output voltage? It is nothing but VCC, that is 5 volt. So let me write 5 volt only. 5 volt minus this IC RC. So IC value you know here. So it is 5 minus this beta RC into VI minus V of BE on by RB. Right. So if you see now
Sir?
this,
Sir, shouldn't be there a contribution of VCE in the output?
VC in the output, actually this output voltage is equal to V of C, na?
Okay. Yes.
Isn't it? See this? This is the voltage now we have taking, and this is the same voltage like V of C is this much only, na?
Yes.
Right? Okay. So now if you see this equation here, this output voltage is coming like this 5 minus beta of this VI minus V of B, this one, right? Now, if you notice these two things, that this output voltage, right? It is 5 minus, first is minus of this V of I, right? It is 5 minus of V of I. So that means as this V of I will now increase, say V of I is changing linearly, then V output voltage will fall linearly. Is this point clear from this equation? Okay, if this part is clear to you, then we can say like in the active mode or in the active region, the output voltage will fall linearly with changing this input voltage. Now the thing is that up to how far it can fall, right? Okay. Now see that when, okay, for this let me again go to this. Right. So transistor will be in the forward active mode till this point, right? Till this Q point. But when the transistor is Q point is now shifts to here, then basically it is going into the saturation region. And in saturation region, in yesterday's class, we have considered that for modern BJT, generally this value is considered as 0.2 volt, right? We have also explained why it is around 0.2 to 0.3 volt, right? So if you consider that the V of C sat is around 0.2 to 0.3 volt, then we can also assume, or we can also say till this V output voltage reaches to that value 0.2, until that point, this this characteristics will fall. Means from here the characteristics will fall and fall till V output is nearly equal to 0.2. Now the question is, at what input voltage the output would be this 0.2 volt, right? So for that, if you just replace this output voltage to this by this 0.2 volt, then you will get it, right? So say if you now replace it with a 0.2 volt. Yes. Yes, please tell it. Please tell me.
Sir, yes. Sir, when V0 is 0, means V output will be tending to 0. Sir, T would be stopped, no, sir?
When okay. Sorry, could you please repeat your question once again?
Sir,
When?
when V0 is less than the starting voltage of VCE, means there would be some initial voltage required to start VCE, no, sir? To get it in forward bias. Oh, means whichever bias it is.
Okay. So let me try to understand your question. You are saying that when this V output is what?
Tending to 0,
When this
VCE would
when V
be
output
also
is
0.
tending to 0. When this V of
Yes,
tending to 0 means it cannot reach 0, but it can minimum go up to that V of C sat, which
yes,
is nearly
yes,
equal to 0.2.
yes. So
Hmm.
at that time, sir, means our assumption would be become false, no, sir?
Which assumption?
This means VC should be in the reverse. Means the polarity of VC should be the polarity of VB should be this.
Polarity of VBE should be
Sir, the first forward active mode, sir. That
for
assumption.
yeah. So you are saying like is your question like why I am writing from here means how in this equation I can write 0.2? Is this your
Yes,
question
sir.
or your
Yes,
question
sir.
is
Yes,
like
sir.
before
Yes, sir.
this equation?
No, sir.
This
This
question.
equation
Okay,
itself.
okay, I
Yes, sir.
understand. Yes, so that is a good question. Yeah, yeah. Your question is in this equation we have derived considering that the transistor is in the forward active mode, right? Then how in this output voltage we can write this V output as 0.2, because when we are writing V output is 0.2, then we are assuming or we are considering that the transistor is in the saturation region. That is because see this is okay. For that I think this would be a good way to go. See, if you consider a transistor characteristics like this, right? So okay, and if suppose the Q point is somewhere like somewhere here, then you can say this is at the edge of like saturation region. This say this Q point. This Q point is at the edge of saturation region. At the same time, this Q point is also at the edge of this forward active mode, isn't it? I mean, we are considering the point where the transistor is just switching from active region to saturation
Yes,
region.
sir.
Okay, this at the edge. So that's why the current value would not be very different. Okay, from this saturation. We have find this equation, and now we are trying to find what would be this input voltage for that. Right. So we can consider here also the current value would be this one.
Okay, sir. Got my doubt, sir. Cleared my doubt.
Okay.
Yes, sir.
So right now to find at what VI this output voltage would be this one. So we have to do this simple thing. Just substitute V output 0.2 phi beta, then this V of BE on, right, by RB. I think I have not missed anything. So from that we have to find this VI. So could you please find VI?
So 0.7 plus 144 by beta.
Yeah, can you give me some number that would be good, like some value? Okay, for that, I think you might need the value of this beta. So, okay, consider beta as 120. Okay, consider beta as 120. Okay, consider
So
beta as
1.9 volt.
1.9 volt. Okay, fine. So if you consider beta as 120, then if you calculate it, okay, from here you find the value of this beta, V of B equal to around 0.7. Then I think this value should come at 1.9 volt. So what is this 1.9 volt? 1.9 volt is the input voltage when the output voltage would become 0.2, right? So you see that 1.9 volt, say this is 1.9 volt, and here the output voltage is around 0.2, right? So if you now connect these 2 points, then that basically gives you this. This is means this line is basically nothing but actually this line, right? This line V output equal to 5 minus beta RC into VI minus this line, right? And it should be this way only, straight line only, right? Because from this equation it is clear, right? Now what will happen? Third condition, if this VI is greater than 1.9 volt. Any comment?
Sir,
The
V dot will
transistor would be in
stay at
saturation.
0.2.
Saturation, right? And in saturation, we can assume that the output voltage will not change much. V of C will not change much. So V of C will be constant at V of C sat, which is nearly equal to 0.2 volt. So then we can say from here till the input voltage is 5 volt, the output will remain at, I think I should have used different color for that. Because that's what I'm doing so far. Okay, number 3 is when this V input voltage is greater than 1.9 volt, then output voltage will be equal to V of C sat, which is equal to 0.2 volt. So from here till this point, we are getting this type of pattern, right? I mean, this type of output. So now if you see for this circuit, the voltage transfer characteristics comes out to be like this. So where we have seen this, in this region, the transistor is operating in the saturation region. This particular region, the transistor is operating in the active mode. And here, till this region, the transistor is in cutoff. Right? So cutoff, active, and saturation. And you can see the behavior of this regions in terms of in terms of output voltage. Fine. Now here one important thing is this active region. This region. I mean, when the transistor is operating in the active region, then this transistor can behave as an amplifier. Okay, when the transistor is operating in the active region, then only this will behave as an amplifier. Why it is amplifier? Because that is also, it should be also clear to you if you think, because here, if you see, this is the input voltage, right? Now, if you make a small change in this input voltage, say you are changing a, like, this much of this input voltage, right? Input voltage is changing by only this much. See what is the change in the output voltage, right? The change in output voltage is this much, right? So because here the slope of this voltage transfer characteristics is greater than 1, right? Here this slope is greater than 1, right? And for amplifier, you need this criteria, right? If the slope is less than 1, then obviously you will not get any amplification there, right? But if you see in this, the other two regions, right? For example, for which color I can pick. I think I have used almost all the colors here. So in the saturation region and the cutoff region, the output characteristics is almost independent of the input voltage, right? So here the outputs are fixed. It not depends on the input voltage. So this cutoff and this saturation, these are used when the transistor is being used as a switch. Okay, when transistor as an, switch means type of mechanical, you can say it is a replacement of the mechanical switch. Like in your home, you have the mechanical switch in your switchboard where you press it, current start flowing. When you make it put it in the other position, the current, the the current stops, and there will be like fan or light that will also turn off, right? That is basically the mechanical switch, but we can use this transistor to do the electrical switching, right? And we will also discuss it briefly how this transistor can be used as a switch as well as amplifier.
Sir,
Huh.
sir, can it be used as a stabilizer?
Stabilizer in the sense like you have voltage fluctuations and then you want to regulate that.
Yes, sir.
Okay, can you give me some idea how you are thinking? I mean, why you are thinking, and what is your plan?
Because sir, here Vi from 1.9 to 5,
Hmm.
sir, the output voltage is constant.
Right.
If we have some fluctuating voltage between 1.9 and 5.
Huh. But what is the output voltage? It is only 0.2, na? Probably that voltage would be too low for your any of your application, right?
Yes.
Okay, so here one more thing is this voltage transfer characteristic we have shown using NPN bipolar junction transistor. So homework is please do the same using PNP bipolar junction transistor. So when you do it using PNP, you will see that this voltage transfer characteristic will change a bit. Okay, so I request you to please do it in your home, that instead of this in NPN, you replace it with PNP transistor and do the same analysis and try to find the voltage transfer characteristics. Voltage transfer characteristics in in short, it is also written as a VTC, voltage transfer characteristics, VTC, voltage transfer characteristics. Now say BJT as a switch. So how can a BJT can work as a switch? No, this is quite easy actually. So you see that you consider a circuit like this where you have actually connected one LED, um, in this circuit like this, and this is one resistance that you have connected to regulate the current which should be flowing through this LED. Now, if you see this, when this VI is less than 0.7 volt, basically this transistor is in the cutoff region, there will be no current, right? There will be no current. If there is no current, then the LED cannot blow, so LED will be off. But if this VI is more than 0.7, say quite high, say this 5 volt, right? Then there will be current, right? The current IC will flow depending on the value of this R and the resistance of this, as well as the voltage drop across this LED. So IC will flow. So now the LED will glow. All right. So that way you can think of like keeping it between these two voltages, or by changing the voltages across this base terminal, you can change the current through a device which is connected with the other terminal, which is the collector terminal. So in that way, you can think that this BJT can also work as a switch, or you can think of replacing some switching action of your mechanical switches. You can probably replace by this BJT circuits. Okay, and remember here the transistor would be operating in basically two regions, either in this saturation region, right, or in the cutoff region, right? These two regions only. Now to briefly discuss about how this BJT can
So
huh?
I don't understand why only two regions means.
Why only in two regions? Okay.
Yes.
Okay, you see here. Suppose you are giving any input voltage less than 0.7. Okay. Then what is the output voltage? 5.
Yes, sir.
Right? Okay. Now if consider you have given a voltage 1.5. Right? This is here. Then what would be the output voltage? Output
Smaller.
voltage you will be getting smaller than this 3 volt, right? So you are giving some voltage, but you are not getting the full output, right? So that means you have the supply voltage 5, but you are not getting 5 volt. You are getting some voltage which is lower than 5 volt.
Yes,
Okay.
sir.
You understood? But if you now consider the voltage higher than say 1.9 volt for this particular circuit, then you see for 1.9 volt, any voltage above 1.9 volt, the output voltage would be 0.2 volt only. Even for 5 volt, it would be 0.2 volt only, right? Which is close to zero, you can say. Obviously, it is not equal to zero, but it is close to zero.
Sir, above 5 volts.
How does this property means make it behave as a switch? I understood that different values of Vi means change V0.
Mhm. Okay, so here, okay, say, okay, maybe in the other way to explain it would be like this. Say this value is not now 5 volt. It is say 10 volt, okay, plus 10 volt. And say we are changing this input voltage from 0 volt to 2 volt only, right? So when you give 0 volt, then what is the output voltage? Say we are we don't have any we don't have LED and we are considering taking only the output from here. Then what would be the output?
10
10
volt.
When you give
Okay.
here 2 volt, what would be the output? 0.2. Right. So you can see that by doing a small change in this input, you can actually produce a big amount of change in this output. Means you are giving here some control signal. That you can think it in that way as well. You can giving here some. You are giving here some control signal, and using this control signal, you are able to control the output voltage, which may be much higher compared to this control signal.
So, sir, Vi can only take some fixed values, right?
In the output or in the input?
Vi input.
In the input. No, VI in the input, yeah, because you, in the input, no. See, here input you can go for higher value as well. Right. Obviously, no, if it is the lower value is, you are considering only the positive one, then the lower value would be expected to be zero only. In the higher value, it is not only 2 volt, but you can go for higher voltage as well, as long as you are in the saturation, and you will be in saturation. If you use higher value than 2, then obviously they will be definitely in the saturation region.
Like we adjust Vi such that it is in forward active region. Then what will happen?
Then what will happen? Yeah, that's what we have discussed here now. So suppose you have adjusted it at 1.5 volt, right, for this particular case. Then it is in the forward active region. Then at the output, what value you are getting? The output value you are getting around 3 volt, right? Say, okay, right? So obviously then 3 volt is now not closer to this 0 volt, neither closer to this 5 volt. That is one thing. So you wanted like I apply some voltage, then the output would be either on or off, right? But you are getting somewhere intermediate. And here one more difficulty would be, suppose instead of 1.5 volt, if you give now 1.6 volt, see, then the output would be now closer to maybe around 2 volt. It will further reduce, right? Because it is in the active region, right? Here the slope is very high. Very small change in this input voltage will result a very significant change in the output voltage.
Okay, sir, understood what you are saying.
Okay, then now how BJT can be used as in digital logic. Okay, so here for to start with, consider a very basic circuit. So consider this circuit here, right? Here, if you give an input voltage here, again says like input voltage is say 0 volt. Say this input voltage is say 0 volt. Then what would be the output voltage? If it is 0, then no current. Output voltage would be VCC. Say VCC equal to 5 volt. Then this would be 5 volt only, right? Okay. Now this is like for a digital logic, right? Digital logic you can apply either high input or you can apply a low input, right? So low input, and say for our high and low, by saying high and low we mean low means 0 volt and high means 5 volt. Then this 0 volt, for when you are giving 0 volt, you are getting this 5 volt. Now when you are giving the input as high, that is the 5 volt, then what is the output voltage? Then output voltage is around 0.2 volt, right? This is will be V of C sat, right? Then you see, if you say in terms of logic, all right, then 0 volt means logic 0 or low logic. then output is 5 volt, which is high logic. Here, this input is high, so it is logic 1. What is the output? Output is 0.2 volt. 0.2 volt is quite close to 0.0 volt. So here we will say that this is the logic 0, right? Because in digital we say like we can apply two voltage, either 0 or 5 volt or the VCC, but you have to also remember we have some range, because it is not possible in actual circuit to apply accurately at exactly 0 volt. It's not possible, right? So you have to always keep some range. Okay, so say like for 0 means say 0 to maybe 0.2 or 0.3 volt. Okay, 0.3 volt, right? Similarly, for 5 means it is not exactly at 5, say like a 5.2. For some, it also depends on the design. Okay, say 5.8 to say like 4.6 volt. Okay, this range. So we have always some range. So if the voltage is within this range, we will consider it as 5 volt and logic high. If it is within this range, we will get it as logic low or logic or 0. Right. So you can see applying output input at logic 0, we are getting at output logic 1, input logic 1, output logic 0. So obviously this is nothing but the NOT gate or the inverter circuit. Right. So this circuit, if you want to use in your digital purpose, then particularly this circuit can behave as a NOT gate or inverter. Right. If you think about the other circuit, which is shown here, so here also consider like VCC equal to 5 volt, right? So if this V input here, there are two transistors. You can see here only one transistor, but now what you have done, you have actually taken this part, right? This is basically this part, and replicate this one here as well, right? So you have another this part, replicate this part as well, right? So you have mirrored it. Right. So here there are two inputs, obviously. So one is VI1. So if you consider this VI1, say first, say like both VI1 and VI2 equal to 0. So say both are at 0 volt, and this is at 0 volt. So when this is 0 volt, this transistor is off, right? This transistor is off means here this voltage would be 5 volt. This transistor is also off, so 5 volt. So 5 volt, right? Mean this transistor is off means you can say like this is no open circuit, and this is also no open circuit. This is not connected with this ground, right? So both are having have a output voltage of 5 volt in this case. Now say you have switched apply 5 volt at this input VI1 and apply 0 volt at this output. So here when you have applied 5 volt, you make this transistor on. So this voltage is now 0.2 volt. Sorry, 0.2 volt, but you have made this transistor off, right? So this voltage is still 5 volt, but see, this V output is connected with this, right, parallelly with both of them. Now this voltage is 0.2, right, which is quite close to this ground. So this V output will be equal to 0.2 volt only, right? So similarly, you can guess like when you apply 5 volt, 0 volt and 5 volt, you will also get 0.2 volt, right? When you apply suppose 5 volt and here 5 volt, right, then both transistors are on, both are at 0.2, so the output voltage would be at 0.2, right? So if you now see in terms of logic, then we can write here 0.
Could you please explain how did the 0.2 volt come? Then one is 5 volt and another is 0 volt.
Sure. Sure. 1 minute. Yes. So your question is like for suppose for one of this case, right? When this is 5 volt, so suppose we have applied 5 volt here, so that makes this voltage as 0.2, right? Whereas we have made this voltage as this voltage we have applied, I think 0 volt, right? So that makes basically this transistor to be off, right? When this transistor is off, this voltage will try to means the current IC would be equal to 0, right? That is the IC would be equal to 0. That is the way we should analyze. IC would be 0 equal to 0 here, right? But here you have a good amount of IC which is flowing through this, right? As a result, this point, the voltage at this point will become 0.2 volt, right? If it is a single transistor, then obviously this voltage will reach till 5 volt, right? But here you have one more parallel transistor which is flowing through, I mean, which is connected in parallel with that, right? So, but IC is 0 for this transistor, but so what? There is a good amount of IC which is flowing through this transistor. As a result, the voltage drop across this transistor, the other transistor would be equal to 0.2. So that also sets the voltage, I mean, that will set the voltage of this particular line to at 0.2 volt only. So as a result, for this case, you will get an output voltage of 0.2. Same thing will happen for this. Is this clear?
Okay, sir. Yes, sir.
You got my point, right? Okay. So you can see like
In
this.
the last case.
Last case is even easier because see here now it is 5 volt, so obviously it is like 0.2. Now here also it is 5 volt, so obviously like you know like both transistors are now conducting, right? So here it will be V of C saturation, and here also it will be V of C saturation.
Yes, sir.
Okay, see the output voltage depends on the drop across this, right? This is like not on the current which is flowing through this RC, because then this for the last case the current flowing through this RC would be higher, right? Am I right? No, current will not change because current will depend on this VCC value. Current through this RC will depend on VCC and this voltage only, and this voltage is not changing. This is 0.2. So that way the current through this RC will not change, neither for this, nor for this, nor for this. Isn't it? Okay, so I think we will start with this how to use BJT as an amplifier, right? But before that, okay, we will take a small break. Huh? So maybe I will stop recording for this video here because it is already 1 hour, right? So the other part I will start recording again once we start after 2 minutes. Huh?